Hello everybody. In the last class we were discussing about the plate boundaries, and now we will discuss about the migration of plate boundaries and the motion of the plates. So let us discuss about the migration of plate boundaries. The diagram that is presented here shows two mid-oceanic ridges with one convergent boundary and two divergent boundary. So divergent boundary is here, here, and the convergent boundary is here. Convergent boundary existing between plate number 3 and plate number 4. So in this condition, if we take into account the geological condition, plate number 2 cannot have its size to be fixed because of the condition prevailing at the MOR here and at the MOR here. The size of the two will go on increasing with pushing of plate number 1 to the left and pushing of plate number 3 to right, and finally this plate number 3 will be consumed at the plate number 4 at the convergent boundary, what has been shown here in this here. So it shows that the plates, they are not constant features over the earth surface. They are found to change their size. Particular oceanic plates are being created and they are being destroyed, but continental plates simply face rifting and union. So this is a case about the oceanic plates. Oceanic plates have been created at the MOR and they are being destroyed at the convergent boundary zones. Thus it proves that the boundaries are not fixed. The lithospheric plate boundaries are not fixed features over the earth surface. They are found to change with time. This has been explained here. So here plate number 2 creates a condition for pushing the plate number 1 to left, plate number 3 to the right, so that the size of the plate number 2 increases and plate 3 faces sinking at the plate 4 boundary to form trench and subduction zone. And we can expect formation of MOR at any place because it is related to mantle convection or mantle plume. Thus, we see at MOR the hot basic magma or lava derived from the partial melting of the oceanic lithosphere or mantle extrudes to form the new oceanic crust or lithosphere at the plate boundary, pushing the two plates away from each other. With movement sideways from the ridge, the new lithosphere cools, becomes dense. With more and more pushing of the plates, the new plates become gradually thicker, denser away from the ridge. It may face underplating as the plates diverge away from the ridge axis. This makes the oceanic plate thick, heavy, as a result of which it starts sinking isostatically into the underlying asthenosphere, causing a condition for convergence. In this process, the migrating plate may reach the edge of another plate where it may bend downwards to constitute a convergent boundary or a subduction zone in order to be consumed back into the mantle, and in this process the cycle runs and the total surface area of the earth is conserved. Because we know if a new plate is being created at one place, there must be consumption of the plate somewhere else so that the total surface area of the earth is conserved. So this happens when the lithospheric plate is being created at the mid-oceanic ridges, and with time, with formation of the MOR, with formation of the new oceanic crust, there must be a condition where this oceanic crust must have to be consumed so that the total surface area of the earth is found to be conserved, and this takes place because of sinking of the oceanic plate at the convergent boundary zones. This has been explained here. Gravity sliding is another factor that drives the oceanic plates to be consumed at the convergent boundary. It is because the ocean floor is thin, shallow at the ridge and gets deeper with distance, and the depth of the ocean is proportional to the square root of the age of the plates. The oceanic ocean increases its depth away from the ridge axis, and also it shows thickening away from the ridge axis. Near the ridge axis, the oceanic plate is very thin, and it is very thick near the convergent boundary or near the trenches. So, because of its thickening away from the ridge axis, the weight increases, and it creates a condition for isostatic settling or for the subsidence of or the motion of the oceanic plate towards the continental plate where it subducts in order to be consumed at depth, so that the newly created crust at the MOR is compensated by the melting of the oceanic lithospheric plate at the convergent boundary zone. And let us know how depth of the sea floor is found to change from MOR to the convergent boundary zones. It is roughly proportional to the age of the oceanic rock away from the ridge. And there is a formula that has been devised by Parsons and Skalter in 1977 in order to account for the depth of the ocean floor from the ridge axis to the trench. So, if the age of the ocean floor is less than 70 million years, in that case the depth in meters is shown by this formula: 2500 meters plus 350 root t root of the t, but t is the age of the rock. Suppose this is the mid-ocean ridge, and we want to measure the age of we want to measure the depth of the ocean at this point. Then we have to see what is the age of this rock, because here it is age is 0. As you go away, the age of the ocean floor increases. So, what is the age of the ocean floor at this point? So, root over of that age gives the depth of the ocean floor in meters at that point, or it is given by this formula. Roughly, it is proportional to the age of the rock. The depth is proportional to the root over of the age of the rock. And if the age, as per Parsons, if the age is more than 70 million years, the formula becomes something different. This is the formula. Or it is calculated by the global depth and heat flow model. Here, if the age of the ocean floor is less than 20 million years, then this is the formula which is being used to find out the depth. If it is more than 20 million years, this is the formula which is used to find out the depth. So, the general concept is that the depth of the ocean is found to increase from the MOR to the trench. So, depth is very low at the MOR because new oceanic crust is being created there. So, this is about the oceanic depth. Then let us discuss how the plates move. As I have already discussed, the plates are curved bodies. The plates are curved bodies. These are not planar bodies. So, when they are moving, their movement is a type of rotation. And this rotation takes place with respect to an axis of rotation, and they must have a pole with respect to which the plates move, and that has been explained through Euler, and this is called Euler's theorem. So, how the motion of the plates takes place, that is explained by Euler. So, let us discuss it. Plate motion is complex because the plates are curved and interdependent. They form the pieces of the cells of the spherical earth. Thus, the motion of the spherical plate on a spherical body is just a rotation of the plate about an axis of rotation. Geometrically, this was first explained by Leonard Euler, a Swiss mathematician in 18th century. So this is, let us say, this is the plate. Originally it was here, plate A, and it has moved to A dash. So what happens to the axis and to the equator of rotation? Let us discuss. The plate A has moved to A dash. This rotational movement has taken place about imaginary rotational axis, which is called as the spreading axis, and the pole is termed as the spreading pole. The new position of plate A dash and A dash, or the new position of the plate is A dash, and this is shown by the point A moving to A dash and the point 2 moving to 2 dash, 2 moving to 2 dash, 1 moving to 1 dash, 2 moving to 2 dash. At the same time, 1 moves to 1 dash, 2 moves to 2 dash. But what happens, as it is a type of curved motion or circular motion, and it is a rotation with respect to an axis, the rate of motion is not found to be constant. The rate of motion here is different from the rate of motion that is here, because at the same time this distance is being covered. So this is smaller distance, this is a bigger distance. That's why we see that plates, the same plate, because of its rotation, it cannot have uniform velocity in all parts of the body. The distance from 1 to 1 dash and from 2 to 2 dash are not the same, but these distances have been covered at the same time interval. This proves the fact that the different parts of the same plate show different rate of motion. The path through 2 points that move define the spreading latitude. This is the spreading latitude. Hence, the spreading rate is 0 at the spreading pole and maximum at the spreading equator. Since the natural lithospheric plates are of different shape, size and location, every plate rotates about an individual spreading axis. The perpendiculars drawn to the spreading latitudes meet at the spreading pole. So here, that has been shown here. So this is the spreading axis, the spreading equator. So perpendiculars are drawn there. This is the perpendicular drawn here, the perpendiculars are drawn here, perpendiculars are drawn here to the spreading latitudes, and they come to a point. These perpendiculars, if this is moving to this, so this is moving like this, this is moving like this. So perpendiculars are drawn to this spreading, these are circular. So perpendiculars are drawn to the circular path. So they meet at a point. So this becomes the spreading pole with respect to which this rotation has taken place. And this is the spreading latitude, or the farthest the distance from the pole will give the equatorial zone of the rotation. So let us see. This is the latitude of rotation. So perpendiculars are drawn to here. This is a perpendicular. Here this is a perpendicular. They meet here. So this is the pole. And through that pole, if we imagine that this pole through the center of the earth is extended downwards, that gives the axis of rotation, and this becomes the pole with respect to this plate for its rotation. So these are the perpendiculars to the spreading latitude which meet at one point. that define the spreading pole. The axis is the line that joins this pole to the center of the earth and extends to the opposite side on the surface of the earth to constitute the spreading axis. So we can expect all the plates to be moving in a circular path, and the perpendiculars to this circular path, they indicate they meet at one point. This gives the pole. This has been discussed here. So this is the pole. If we draw perpendiculars to this side, perpendicular to this, they meet at this point. So this is in this manner the plates face movement. So plate motion is not a straight motion, it is a circular motion, and all parts of the plate do not present uniform velocity, and the velocity is found to be more towards the spreading to the latitude of rotation, and the rate of movement or the velocity of plate motion is nearly zero at the pole of rotation. This has been discussed here. So this phenomenon has been explained by Euler, and simply we should remember that as these plates are curved bodies, they are moving over a curved surface, their rotation cannot be a straight line, it will always be circular, and that will be correlated to a pole of rotation. And this explains the Euler's theorem, and this proves the fact that the plates do not have uniform velocity in all parts of their body. So this is about the plate motion, and now we will discuss about the causes of plate motion. What are the different causes? We know that convection current is the main mechanism that accounts for the plate motion, and this convection current causes the ridges to be fall, ridges to push, and because of thickening of the oceanic plate towards the trench, there occurs slab pool, as a result of which new crust is created at the ridge. It is being consumed at the convergent boundary with the oceanic plate or continental plate. So if the magma is coming up, it is forcefully coming up at the MOR, it tries to push the plates in two opposite directions. So the plates get the force to be driven over the asthenosphere. So this is the ridge push. And slab pull, because the oceanic plate becomes denser and thicker towards the trench, it becomes heavy, and the slope is almost from the ridge axis, the slope is towards the trench. So slope is there, a thickness is also increasing, so it is being dragged into the asthenosphere. So this is slab pull. So slab pull, ridge push are the two mechanisms by which the plates newly created at the MORs can have their motion. Besides these, we have the ridge push, here the rise of the hot mantle material or magma lava below an ocean ridge produces a large low density bulge which exerts lateral gravitational pressure on the plates on either side. This is the ridge push mechanism. The magma added to the margins of the plates get welded to it with rifting in the middle corresponding to the plate boundary and drifting from the ridge axis in opposite direction as magma extrudes. Extrusion goes on, taking place along the ridge axis. So forceful extrusion of lava at the ridge axis will create a condition for plate motion on both directions away from the ridge axis. That is the ridge push. Beside that, we have the ridge pull mechanism. We have the ridge pull mechanism or this slab pull mechanism. Here, the gravitational effect of the cooler denser material in and around the sinking slab of the oceanic plate. As the denser plate descends down at convergence boundary, its weight pulls it downward to be subjected onto the overriding plate. Here, another factor that promotes slab pull is the slope of the sea floor from the ridge to the trench. Ridge site is shallow and trench site is deep, and therefore, with edging, with the edging of the ocean plate, the density and depth increases, promoting subduction. Besides the above two mechanisms, there is third mechanism, that is mantle drag or the convection current, corresponding to the spreading of the convective flow below the lithosphere. So, if this is the lithosphere, the convection current causes the plate to be lifted and plates to be drifted. So, flow below the lithosphere drags the overlying plate. It is known as the convection current. It is known as the convection current which rises. This convection current which rises and upwells at MOR, which rises and upwells at MOR and laterally spreads from the ridge axis below the lithospheric plates. So, because of its lateral spreading, the convection current below the oceanic lithosphere, rifting takes place. This plate moves this direction, along this direction, this plate moves along this direction, because some amount of the rising convection current moves laterally, dragging the overlying lithosphere in two opposite directions. So, during this lateral spreading of the convection current, there occurs the dragging effect of this current on the overriding lithosphere, as a result of which it is dragged away from the ridge axis to the trenches here. So, this is causing dragging. This is causing dragging of the lithospheric, particularly the oceanic plates, to the trenches where it is consumed, because new crust is being created here. As surface area is constant. So, if a new crust is being created here, somewhere the crust will have to be consumed, so that the total surface area of the earth is consumed. So, here it is being consumed, here it is being created, and this convection current mechanism drags the continents, drags the new oceanic lithosphere along two directions, which are finally consumed at the convergent boundary zones. Now, let us discuss what is mantle plume and the hot spots. Mantle plumes, they originate from lower mantle or from the mantle core boundary. So, mantle plume is the column of abnormally hot, buoyant rock or magma that rises from the deep in the mantle, which may be the core mantle boundary at 2900 kilometers depth. It pushes its way through the partially molten material and tries to lift up the overlying rock column, creating stress and tension by upward arching or doming up of the crustal material. It may lead to rifting, formation of rift valleys and triple junctions. When it first hits the lithosphere, it may give rise to the large igneous provinces such as Deccan traps, Siberian traps. These are the traps which have been produced because of mantle plume. Deccan traps has been produced by a mantle plume, and similarly Siberian traps. So, these mantle plumes that rise from the core mantle boundary in form of columns rises up, pushes the lithospheric plate upwards, causes it to be lifted up, as a result of which it is being domed up and tension, cracks develop that ultimately results in triple junction, and in some cases they simply extrude to form the traps. So in these cases it is found that there has not been, so where the traps are being produced, it is found that there has not been any plate motion during the formation of these traps. These are the plumes coming from the mantle core boundary. It gives rise to the flawed basals that form the traps. There are other cases where there is plate motion over the mantle plumes, so that the superficial expression of the plumes are seen in form of volcanoes. These volcanoes that result from the mantle plumes are called the hotspots. Thus, superficial trace of the mantle plume is the hotspot. Hence, it can be said that mantle plume is the engine that causes the hotspots. Intraplate volcanism through the hotspots produces a chain of islands that indicate the direction of plate motion. So, the mantle plumes originate from the mantle core boundary. It comes up and lifts the lithospheric plate to form arc, create cracks, tension, and final lifting and drifting. Or it may extrude to form the traps. When it is forming traps, there we can say the lithospheric plate has not faced any movement, because of which the extrusion of lava is taking place over the lithospheric plate in a particular region. As we see the Deccan traps, the entire the south part, this part is represented by the lava flows, and this lava flow has been contributed by the reunion hotspot. So, Indian plate was near the southern end of the South America. It has migrated from that place to the Eurasian plate or the Chinese plate, and finally it has collided with the Chinese plate to produce the Himalayan mountains. While its motion from the southern tip of South America to the China, during this motion it has passed over this reunion hotspot that has given rise to extrusion of lava, and that has produced this Deccan traps. And Deccan trap volcanism has not taken place in a single phase. Several phases of volcanism has been there, and because of which the traps have been produced. And the hot spots, they provide the site where mantle plumes are found to come out in form of volcanoes. So, hotspot is the superficial expression of mantle plumes. As we know, the plates are not the fixed bodies in the earth surface. The plates are in motion with respect to one another, and mantle plumes are generally found to be fixed in their location. So, when the plate is moving over this mantle plume and extrusion takes place over the moving lithosphere, so a mountain like mass is being created over the lithosphere, and if it moves further, mantle plume is having its fixed location, so the plate will come over here. This will be the first volcano, then another volcano will be created here, then plate will move. So we will have here it is one volcano, here is another volcano, and another volcano will come up here. So as we go away from this hot plume or mantle plume, we see the age of these volcanoes increases, and nearer the hot plumes the age of the volcanoes are very low, and as you go away from the mantle plume, the age of these volcanic mountains increases. And this has been seen in a number of volcanic mountains that are seen in Pacific Ocean. They form a chain of islands, and these chain, they indicate the fact that the Pacific plate has moved over the hotspots, over the mantle plumes or the hotspots. And this plate motion has produced some of the major island chains such as Howland Emperor chain of islands, Line Islands, Austral Cook Islands, Lausaville chain of islands. And all these island chains are found in Pacific Ocean. So this is the Hawaiian chain. This is Austral plate chain here. Hawaiian Emperor chain, HE. This is Hawaiian chain of volcanic mountains. Then AC, Austral Cook, AC here, this one. These are the volcanic chains, the Austral Cook volcanic chains. And we have Line Islands, LS, Lausaville chain, OP. So these are the number of volcanic chains, and their orientation shows that the movement has taken place, movement of the ocean plate has taken place along this direction. The orientation, the parallelism shows that the oceanic plate has moved along this direction. So hotspots, they form the volcanic chains of mountains, and as the mantle plumes are found to be fixed and the lithosphere plates move over it, we find a series of volcanic islands. So we find these volcanic mountains in the Pacific Ocean. They form more or less parallel chains indicating the direction of Pacific plate motion. The hotspots are not always found to be linked to the deep mantle plumes. There may be shallow mantle processes in form of small scale mantle convection that may cause hotspots. The site for extrusion of lava or magma to form islands, generally in a chain. If the volcanic chains of islands are very closely spaced, they give rise to aseismic ridges, as we have seen in 90-degree east ridge in Indian Ocean. We have the Indian plate here, 90-degree east longitude. This line here, we find a number of volcanic islands. They are closely spaced. They form the aseismic ridge. Besides that, we have the Greenland Scotland ridge in North Atlantic, Rio Grande ridge, and Wabash ridge in the South Atlantic Ocean. These islands are associated with broad coastal swells causing lift of the earth's surface. Compositionally, these islands are tholeiitic basalts that form the bases, with alkali basalts in their upper parts enriched in sodium and potassium. Compared to mid-oceanic ridge basalts, these tholites are having higher concentration of iron, titanium, barium, zircon, and rare earth elements. They are underlain by thickened crust and thin lithosphere. So this is about the hotspots and the mantle plumes. So mantle plumes give rise to the volcanic islands, and most of the hotspots are located in Pacific Ocean. Some are located in Atlantic Ocean. So major volcanoes are seen in Pacific, and they are related to the hotspots. Hotspots are nothing but they are the superficial expression of the mantle plumes, and mantle plumes originate from the mantle core boundary. So let us see what are the hotspots of the world. These are some of the hotspots of the world. In Pacific Ocean we have the Bowie, Cove, Hawaii, Cicero, Galapagos, Marquesas, Samoa, Pitcairn, San Felix, Society, Austral, Easter, Juan Fernandez, Loiseville, Yellowstone. It is found within the continent in North America, and Caroline. So these are the hotspots which are found in Pacific Ocean. And in Atlantic, Jane Mayen, Iceland, Azores, Bermuda, Canary, New England, Cape Verde, Fernando, Fimando. Then Ascension, St. Helena, Martin Vaz, Tristan, Discovery, Shona, Bouvet. These are found in Atlantic Ocean. Then Indian Ocean, Comores, Reunion, Marion, Crozet, Kerguelen, Tasman, Balani, Lord Howe, Afar. So these are some of the hotspots. So these are the spots where lava extrudes either to form volcanic mountains or to form triple junctions. This Afar hotspot has given rise to Afar triple junction. So these are the hotspots in Pacific Ocean. These are the in Atlantic Ocean, Pacific Ocean, in Indian Ocean. So these hotspots and mantle plumes, they indicate the fact that the plates are not fixed bodies on the Earth's surface, they are having their movement, because of which series of volcanic islands are being created depending upon the direction of plate motion. Then let us see what is triple junction. A triple junction is the meeting point of three plate boundaries. It may have any combination of the boundaries. The boundaries may be trench, ridge and transform fault. So any combination of these three can be expected in a triple junction. And the ridge type, they form the most stable junction. There are 16 possible triple junctions, out of which ridge triple junction, or the junction between three ridges, are stable. Also, when three boundaries that are made of ridge, trench and transform fault, it may give rise to a stable junction. So how the junction becomes stable, that we will discuss. Let us see some of the triple junctions. Azores in Atlantic, Galapagos in Pacific, Afar triple junction over the Afar hotspot, Bouvet triple junction, Easter Island triple junction, Mendocino triple junction, Indian Ocean triple junction. Then we have the Chile triple junction and Middle America triple junction. In the possible combinations are ridge type, fault type, trench type, ridge fault type, ridge trench type, ridge fault type, ridge trench type. So these are some of the types, and these geometrical and their geometrical variations, stable versus unstable, give rise to 16 possible distinct types of triple junctions. And let us discuss how a triple junction is found to be stable. So triple junction is the junction made up of three types of plate boundaries. They may be ridge type, they may be ridge trench fault type, they may be mixture of ridge trench and fault type. So 10 common types and the geometrical variation make another 6 types. So 16 distinct types of possible combinations of the triple junctions are expected. So in order to study the stability of the temporal junction, we have to consider two factors: velocity vectors of plate motion, which must make a triangle, and the velocity lines must meet at a point. Then only the temporal junctions can be the stable temporal junction. So we have to establish the velocity vectors, draw the velocity vectors indicating the direction of plate motion, and the velocity lines, if they meet at one point, in that case the junction becomes stable. So let us see how this velocity line and velocity vectors are being drawn. Velocity lines always run parallel to the boundaries. Velocity vectors are parallel to the direction of plate motion. Let us now draw the velocity vectors and velocity lines for three types of boundaries. Let us say if it is a trench. So B is moving below A. So A is stationary, B plate is moving. Here A is stationary, B plate is moving down A. So here the velocity vector will be, from stationary plate along the direction of motion. So A is stationary, the velocity vector will be along this direction, because along this direction the movement is taking place, and A is stationary, so movement is taking place in this manner along B direction. B is moving like this. So this is the velocity vector, because along this direction the movement is taking place. A is stationary, B is moving. That's why this is B is shown with the arrowhead and A is with a point that indicates A is stable, B is moving. So B is moving below A, direction of movement is towards east. So AB direction. This is AB direction or this direction. And velocity line is parallel to the boundary. Boundary is like this. So velocity line will be like this, and velocity line will always pass, here in this case will pass on the head of the plate in which direction the motion takes place. Here A is the plate, along this direction the movement is taking place. So over the A head the velocity line will be aligned, and it will be aligned along the direction of the plate boundary. So velocity line will be over A, and this is the direction of velocity. This is the velocity vector. Velocity vector is shown by a solid line, and velocity lines are shown by dotted line. So velocity line will be on the head of the plate along which the movement is taking place. Velocity, and it will be parallel to the boundary. So AB line, this AB line is the velocity line, and this AB solid line indicates the velocity vector. Then another example of trench we can take. The movement is having along this direction. B is stationary, A is moving, so B is stationary. Movement is along this direction. So B, this is the velocity vector, and the velocity line will be along this direction, because this is parallel to the boundary. So velocity line will be parallel to the boundary, and it will stand over the plate along which the movement is taking place. So it will be over the B head here. So this is the velocity line. This we have to remember. If it is a ridge, in that case velocity line will be in the middle of the velocity line will pass in the middle of the ridge is moving like this. So this line will be the velocity line, so this solid line, and this line will give the velocity. Now this will give the velocity vector, and this line parallel to the boundary will give the velocity line. So BA is the velocity vector, and AB passing through the middle of this velocity vector is the velocity line. In case of transform fault, both velocity vector and velocity line run parallel to each other. This has been shown here. Now let us analyze how a triple junction is found to be stable. I have already discussed that the velocity vectors must make a triangle and the velocity lines must meet at one point. Velocity vectors must make a triangle and velocity lines must meet at one point. In that case, it will be stable. This fact we have to remember. Let us analyze A, B, they are having A, B, C, they are having ridge type of boundary. Ridge type of boundary. So velocity line, velocity vector will be BA like this. Will be like this. Then AC, BC like this. Then AC like this. This has been shown here. This is triangle. So first condition is satisfied. They are making a triangle. The velocity vectors, they make a triangle. We have to fit these velocity line vectors to form a triangle. These three vector lines make possible a triangle as shown above. So their velocity lines will be parallel to the boundary and will pass through the middle of the velocity vectors. So in this manner velocity lines. So when we draw the velocity lines, they meet at the point here. So this is a stable junction. Here we have trench, ridge type. Trench and ridge. So ridge velocity vector will be like this, BA. And if it is moving along this direction, A is stationary, C is moving and the direction of movement is along this direction. This has been. So A is stationary, movement is along C direction, AC. This is vector. Similarly, this vector will be between B and C. B is stationary, C is moving, B is stationary, C is moving. So BC. And here the velocity line will be parallel to this one and it will pass through the B, because along the B direction movement is taking place. So B head will contain the velocity line. Similarly here A will contain the velocity line. So when you combine together, this becomes the combination. So the velocity line they join at one point, so it becomes stable. So in this manner we analyze all these. This has been in the same manner it has been analyzed, and whether they are stable or unstable. Here the point is occurring here at one point. So stable, they are making a triangle and they meet at one point. Velocity lines they meet at one point. So stable. So here we see that we do not find the formation of a triangle. Triangle is not possible here. And velocity lines they do not meet at one point. So it is unstable. Similarly, this is also unstable because they make a triangle no doubt, but the velocity lines they do not meet at one point. That's why it is not stable. This fault type. So we have to see whether these plates forming the triple junction, their velocity vectors are making a triangle, and the velocity lines making their meeting point at one point. In that case it will be stable, otherwise it will be unstable. Now we will discuss about the deficiencies of the plate tectonic theory. The theory explains about the younger ocean floors. Plate tectonics speaks about the formation of the new ocean floors and the activities of it than that of the older continental plates and on their activities. So plate tectonics especially deals with the formation of the new oceanic crust destruction of the oceanic crust at the trenches. Ridges are found to develop in the mid of the oceans of the Atlantic and Indian Ocean, but not found in Pacific. Here it is on east side of the Pacific. And creation of new crust is taking place in most of the ocean basins, but destruction is taking place only in Pacific border. So this is one kind of deficiency. Young trenches present sediments in undeformed state, which cannot be expected due to convergence. Young trenches, they present undeformed sediments. The trend of the few strike slip faults are not found to be parallel to the direction of movement of plates. Example, faults around Pacific margin, the Alpine fault of New Zealand, Denali fault of Alaska, Atacama fault of South America. The plate tectonics theory shows north-south motion of the plates for east-west trending mountains such as Himalayas and Alps. But magnetic data shows that the plate motion was east-west during their orogeny. These are some of the deficiencies of the plate tectonics. Paleomagnetic data indicates large-scale bending of the plates, but it was said that plates are rigid and brittle. As I have discussed earlier, the plates are the rigid bodies and they are brittle, because of which they have been broken. And below it we have the asthenosphere, which is partially in fluid state or in ductile state. So lithosphere is rigid. If it is rigid, how can it bend? So this is a type of deficiency. African plate is under compression as it is bordered by divergent boundaries at mid-Atlantic ridge and Indian Ocean. Again, it is having East African rift system. All these motions can be possible only if mid-Atlantic ridge, East African rift zone and mid-Indian ridge are displaced laterally. So these are some of the deficiencies. And we have the andesitic volcanoes, characteristics of convergent boundary zones, and they are found far away from the subduction zones. Andesitic volcanoes, such as andesitic cones of western USA, where andesites are located 16 kilometers inland from the coast. We have discussed the andesite volcanoes are the product of convergence of ocean-ocean plates or ocean-continent plates. So normally we should expect that the andesitic volcanoes are located near the trenches, but the andesitic volcanoes which are away, much away from the trench, they are or they cannot be explained in terms of plate tectonics. This is one kind of deficiency. So these are some of the deficiencies, but we know that convection current is the main mechanism that breaks continents, unite continents, produces a new lithosphere, consumes the oceanic lithosphere, and because of this process, throughout the geologic time, we have seen that the continents are found to get united to form single landmass, and they are found to be dismembered to form separate continents along with formation of new oceans between or among them. So now let us discuss the merits of the plate tectonics. It accounts for the distribution of land and sea, continents drift and form the new oceans. It explains about the origin of all mountain belts, pole mountains, the tertiary mountains of Andes, Rockies and Himalayas. These are the tertiary mountains. It explains about the earthquake zones, volcanic beds and their distribution. It accounts for the formation of new ocean basins, sea floor spreading on the basis of magnetic data obtained from the ocean floor. It explains the origin of the mid-ocean ridges, aseismic ridges, hotspots, mantle plumes, epiorogenic movements, orogenic movements. All are explained through plate tectonics. It explains about the breaking up supercontinent into continents and their union again to form supercontinents through Wilson cycle. So what is Wilson cycle or supercontinent cycle? Let us discuss. Throughout the history of the earth, there has been 7 to 8 cycles of supercontinent formation at a time interval of around 500 million years for each cycle. So supercontinents break because of the following reason. The continents do not allow the crustal heat to be conducted. It acts as a blanket for the heat. The oceanic crust allows conduction of heat, but continental crust does not allow this heat to escape. Therefore, heat accumulates below the continents over years, making the mantle to swell through deep mantle plumes or convection current below the continental plates. When continents occur at a place for a long geologic time, for a long time, this causes the swelling of the mantle plumes, convection current, as a result of which the lithospheric plate lying over these swelling convection currents face rifting. It causes rifting of the continents. Drifting of the continents depend upon the direction of spreading of the mantle convection, and in this process oceanic ridge forms with the formation of oceans. Spreading of the ocean floor occurs for some time till the situation is balanced as Earth's surface area is conserved. Ocean floor gradually becomes cold, old, dense, thick with age and starts sinking over the astrosphere, causing convergent boundary. Thus start the process of closing of the sea. Finally, there occurs the collision of the continents, suturing of the continents to form supercontinent. This is the supercontinent cycle. This diagram shows. So this is the supercontinent. Then it, because of the convection current that develops below this, rifting takes place. Rift valleys widen, narrow ocean develops, and in the middle the mid-ocean ridge comes up. The continents are dispersed continents. Then it becomes thicker. Mature ocean, subduction begins. It starts subducting, and this undergoes subduction, and it pulls the continents towards each other. The sea is being closed, sea gets closed, and again new continental mass is being produced, or supercontinent is being produced. So this is the cycle. So supercontinent, it's rifting of supercontinent to produce continents. Between them the mid-ocean ridges come up, new oceans are being created, oceans enlarge, ocean becomes old, thick, dense, undergoes subsidence, pulls the continents together again to form the union of continents. So this is the supercontinent cycle, and this cycle repeats in every 500 million years time. And the last union of the continents was Pangea, and this dismembering has taken place to the present position, and now the Pacific Ocean has started closing with the expansion of the Atlantic Sea, and time will come when the oceans will close and continents will be brought together to form a single landmass with one sea around them, as it has happened during the time of Pangea towards the end of the Paleozoics. So this is all about plate tectonics, and I think I have tried my best to explain in the most possible manner, to explain what is plate tectonics, how plates are being produced, how plates undergo movement with respect to one another, what are the different types of boundaries, how the hotspots, triple junctions, they play their role, and what are the deficiencies of the plate tectonics, how the plates undergo motion, that has been explained through Euler's theorem, and what are the causes of plate motion. So all features of plate tectonics I have discussed. I think it will be useful to you. I thank you all for giving a patient hearing. Thank you.